Okay, so I think it's time to get started. I hope you're all well fed and ready for some new presentations. I'm Eric. I'm a core developer at Timescale, and we're a small startup. We've been developing a time series database based on Postgres. So this talk is about how we actually re-engineered Postgres to work better with time series data. And since this talk is a lot about time series data, I want to talk a little bit first about what it really is. So time series data is really recording the change of your world. That's kind of different from maybe how you think about data otherwise, because that might more store the state or the current state of the world. So this is more about recording the change. And time series data is recording every data point as a new entry. So this kind of changes how you think about databases and how you engineer databases. And we find today that time series data is pretty much everywhere we look. So many people are probably familiar with this sort of data center DevOps case where you're doing lots of monitoring and metrics of your servers in the data center. So that's one very common area. But there are a bunch of different other areas, like financial, for example. You have lots of tick data, or industrial machines where you have sensors on your machines that manufacture your products. You want to make sure that the machines work well or tuned. You can do things like predictive maintenance in case you want to make sure that if something breaks, you actually know almost beforehand that it's going to happen. You have web and mobile events. You have like push notifications. You want to check what your user's doing in your app. You even have derived or inferred data in AI or machine learning models. In transportation logistics, you might put sensors in your shipping containers to monitor the products you're shipping to make sure that they're stored properly and not destroyed during transport. And of course, in energy and utilities, you want to make sure that you're optimizing your energy production and also usage in your home or house or whatever it is. And time series data is very popular today. It's growing. And this is also shown by the fact that we've been able to sort of grow our user downloads really quickly just during the past 18 months or so that we've been developing the database. So this also reflects the interest in the area. And recently, we've actually released a 1.0 version of our database, so that signifies that the database is production ready. And we have a bunch of different users across the world and across different fields. So in financial, traditional telcos, broadband companies, even some supercomputing companies. And they use TimescaleDB to empower their organization to analyze the past, understand the present, and predict the future. And the reason they're interested in time series databases is that existing databases don't work really well with this type of workload. If you look at the traditional relational databases, they don't scale very well to this workload because you're dealing with a lot of data. So many people turn to NoSQL databases. And they typically exist because they want to solve the scaling problem. So that's good. But you're also giving up a lot of power when moving to NoSQL databases. They typically have their custom query languages that are quite restrictive. So if you're used to SQL, which is by far the most common query language, then you can't use your skills in the same way if you're using a NoSQL database. And you're also creating these data silos. So instead of having a single database where you keep all your data, whether it's time series data or traditional relational data or something else, then you now need two databases. And that adds complexity to your backend. You need multiple query languages. And if you want to join this data together, maybe you want to join your time series data with some metadata, You might have metadata about your sensors that you're collecting data from. Then you have to do that in the application layer, and you don't get that support from the database to do these kinds of joins. But we need to solve a problem here. So relational databases are hard to scale, and TimescaleDB is built on Postgres, which is a relational database. So there's a fundamental problem here. So we ran some experiments to insert a lot of time series data into regular Postgres instance. And this is what happens. We start out, we have like 15K rows per second. But after a couple of hundreds of millions of rows of data, performance quickly degrades, and to the point where it eventually becomes really, really bad. And if you're dealing with time series data, then your write performance is really important because you're continuously writing new data all the time. So it's a very, very important metric. It's much more write heavy compared to many other traditional workloads. And the reason for this mostly boils down to how we deal with indexes in these databases. Especially if you have indexes on secondary columns. Let's say you have a device ID to know which sensor you're collecting data from, for example. So when you start to insert data into the B tree in this case, which is the data structure used in the index, then at first everything's fine because you have enough memory to keep this cached. But eventually you start to write to different pages and you need to start swap them in and out of disk because you don't have enough memory. And because writes, especially to secondary columns, go to random places in this index, you have this kind of swapping behavior where at some point it just doesn't scale anymore because these indexes, they don't fit in memory. So the question here is whether there's a better way to do this. And that's why we created TimescaleDB. So what you get is a scalable time series database with full SQL support. And it's engineered as a Postgres extension on top of Postgres. It's actually not a fork. You can just take your existing Postgres installation and you can install our extension and you're ready to go. So you have SQL for time series. You have pretty much zero learning curve if you come from the SQL world because we support full SQL. It's basically Postgres in that regard. We can also leverage existing tools and connectors. So everything that connects to Postgres also works with TimescaleDB. You can enrich your understanding of data because we support powerful queries including joins. Which is not something you typically have in NoSQL databases. And you have the freedom to design your own data model that fits your application. If you look at the NoSQL world, many people say like, yeah, I like NoSQL because I don't have to define my own schema. I just write data and I'm good to go. And that's great if it fits your particular use case. But what actually occurs is that there is a schema. It's just the fact that it's one schema. You can't select which schema that you want to use. So you have to shoehorn your data into the schema. Here we have the full freedom to pick our own schema that fits our own data model. So with TimescaleDB, you also get scale and performance. You can ingest millions of data rows per second, data points per second, up to hundreds of billions of rows. And it's easy to scale up and out, and I will talk more about this later in the talk. And I will also talk about some performance benchmarks we've done against other competitors or traditional databases, and show that it's mostly faster or equivalent in performance for some queries. We're proven and enterprise ready, so we inherit 20 plus years of Postgres reliability. We support things like streaming replication, high availability, backup and recovery. And on top of this, we've added support for data lifecycle management. So we can do things like continuous queries, retention policies where you want to drop data after a certain time, and archiving. And of course, we have enterprise-grade security as well, because we're built on top of Postgres. So comparing to Postgres, this is the type of performance difference you can see with TimescaleDB. With TimescaleDB here shown in red, you get up to 20x performance improvement for this particular use case. Again, we see Postgres with the degrading performance over time here as you insert more data. And because we're inserting about 100,000 rows per second here, and we're doing 10 metrics per row, that translates up to about 1 million metrics per second. So there's a significant difference. And if we compare to other databases, for example, MongoDB, we see that we have 20% higher inserts. And on simple queries, maybe just querying for one metric or one column, doing simple roll-ups as summation or average or something, then we're pretty much equivalent for these simple queries. But if you're looking at more advanced queries, maybe you want to group by time or do some kind of time bucketing, calculate the average temperature every 10 minutes or so, then we're much, much faster, up to 1,500x almost. And if you want to just get the last point of data, we're up to 100x faster. Compared to Cassandra, it's even a bigger performance difference. We get 10x higher inserts. And in terms of queries, we're faster across the board. For time order group bytes, it's almost 2000x. And if we look at InfluxDB, which is kind of the most well-known time series database out there, then we see that for very simple use cases where you have very few metrics or you have low cardinality data sets, then InfluxDB is typically faster because they're highly optimized for this use case. But it's not by that much. And as soon as you start to move into more complex data, maybe you have many columns of data per timestamp. So you're not only measuring temperature, you're measuring temperature, humidity, maybe some other things that you're sampling each time interval. Then it becomes a lot more complicated for InfluxDB. And here is where we shine, because relying on the foundation built by Postgres and the optimizations we've done on top of that, you can see a lot better performance compared to InfluxDB. And for queries, we see with group bys and time order group bys, we're much faster when you look at more complex data sets. And if you want to do some cost comparisons, so here we ran some experiments with a 30-node Cassandra cluster, because that produced pretty much similar performance to a 3-node TimescaleDB setup. And this is like a streaming replication setup that we use with TimescaleDB. So you have 3 equal replicas. So the write throughput is faster with TimescaleDB. And we can probably do faster queries as well, even though we're have a much smaller cluster. So obviously that translates to like a 10x difference in cost per month, which is pretty significant. So to summarize here a little bit about the performance. So we see that we have faster inserts, especially when we look at higher cardinality data sets. We have orders of magnitude faster queries when we do more complex things than just simple roll-ups on one column. And otherwise, we are pretty much equivalent in terms of performance, sometimes slower, sometimes faster. So how do we do this? How can we make Postgres scale to these types of workloads? And here it's important to realize that time series workloads are different than your traditional workloads that you have in relational database. So if you look at OLTP, which is the common type of workload, you typically see updates to multiple primary keys. So the canonical example here is a bank transaction. You go into one part of your data set, you withdraw some amount from some bank account, you take that amount and you add it to another bank account. So that involves 2 primary keys. In time series workloads, however, It's primarily inserts, not updates. And you write to recent time intervals, so it's it's associated with some kind of timestamp. So how does this work? So to explain this, I'm going to sort of walk you through an example. So let's say we deploy sensors in various buildings where we collect some maybe temperature readings, humidity, or whatever. So we have this data coming in from various sources into a database. So what we do is something we call multidimensional partitioning. We do this in both sort of a time and a space dimension. So we start by slicing things up in the time dimension. So basically, we define an interval. Either you can do it manually, or you can let the system derive one for you and adapt it later on. So we partition on time. And then you can, in addition to this, partition on what we call a space dimension. So for example, on a device ID or building ID or whatever. And you can actually add any number of dimensions that you can partition on to do more fine-grained partitioning. So what we end up with is something we call a chunk, which is really a subtable in Postgres. So it's its own table. But we want to make this easy, because if you have lots of subtables, which table do you write to? So we implemented a very optimized sort of insert path where we route rows or tuples of information to the right chunk. And if there's no chunk or subtable available for that particular time interval or partition where we're inserting data, we auto-create it for you. And even as time changes, maybe you add more sensors. You deploy temperature sensors in more buildings. So your data set increases in size or density, or your data rate increases. So all of a sudden, maybe that time interval wasn't such a good choice anymore. So the system can adapt that for you, so more recent time intervals will be shorter. But this sounds kind of advanced. But that's why we built what we call the hypertable abstraction on top of this. So the idea with the hypertable abstraction is that you should think of it as a regular table. You shouldn't have to worry about all this partitioning. It's happening kind of underneath the hood. And we support almost all common commands or functionality on regular that you're used to on regular Postgres tables. So that includes indexes, triggers, constraints, foreign keys, and upserts. The upserts are these on conflict, do something else statements. And even table management commands. So if you want to change your schema, you want to add a column or something, that's supported, and it trickles down to individual chunks. So to get started, it's pretty simple. You just define your regular Postgres table with a create table command. In this example, we have a time column, a temperature, humidity, and a device ID. So then you only need to issue one single command, which is the create hypertable command, to turn this table into a hypertable. So you give the name of the table, you give the time column using the default time interval in this case, and then a secondary space partitioning column, which is the device. You create 4 space partitions. And then you're immediately ready to insert data. And in this case, when you created the table, there are no chunks, so you inserted one row, that must have created one chunk. And then you're immediately ready to query that data as you would normally do, and of course the data is returned again. But some of you might now wonder, and if you're familiar with Postgres, that there's something that was introduced in Postgres 10 that's called declarative partitioning that sounds kind of similar to what we're doing. And yes, there is some similarities between these two systems because they're built on the same foundation. But there are major differences. So here's a quick comparison. So declarative partitioning, it's optimized for this OLTP type workload that I described before. So if you have maybe 10 to 100 partitions, maybe you partition or shard your data on a customer ID or something, which is very common. Then maybe you have 10, 20, whatever partitions. And these are fixed. So you don't have any auto creation, so you have to create these partitions manually, but that's fine if you just have 10 partitions and then they're fixed. And there's some optimizations built around declarative partitioning for how you join data in partition tables, etc. In hypertable partitioning, however, we're optimized for time series and the workload I've been describing in the beginning of the talk. And we support thousands of partitions because that's what you need if you're dealing with this type of data, because you're moving forward in time and creating new partitions all the time. So you also need auto creation, which we're doing. And on top of this, we've added a bunch of query optimizations to make use of this partitioning, because we have a very sort of opinionated way of doing partitioning that allows us to make assumptions about how the data is stored, and therefore we can also do a bunch of optimizations around this. And I will talk more about this later. And we've ensured that it's very easy to use and set up, because if we would add a lot of additional steps to set this up or configure, then people wouldn't use it. So we made it sure it's very easy to use. And there's even a major performance difference if you look at Postgres 10 with declarative partitioning compared to TimescaleDB. So here we show some insert performance, and on the x-axis we have the number of sub-partitions. And you see that with declarative partitioning, the performance pretty much goes off a cliff pretty quickly, maybe even after a couple of hundreds of partitions. And the reason for this is that the way the Postgres people engineer this is that every time they insert data, even if it's just one row of data, they open all of these subtables for reasons that are unclear, but they do some statistics and stuff. But clearly, it's unnecessary to open 1,000 subtables if you're just inserting in one of them. And that comes with a huge cost. And of course, it doesn't scale. In TimescaleDB, we've engineered this insert path to be optimized for time series workloads. So we're only opening the sub-partition, or chunks as we call them, that you're actually inserting into. And we keep them warm and cached in memory. And since you're typically inserting to the same recent time interval, it's often the same chunk all the time. If you want to use declarative partitioning and set it up, this is the equivalent amount of work you need to do to the setup I showed previously with one create hypertable command. And this is only to set up the first time interval. So every time you move out of this time interval, you need to run these commands again for a new interval. So it's clearly a lot of manual work involved. And if we're looking at repartitioning, it becomes even more of a nightmare. That's actually quite easy with TimescaleDB. You just set another time interval. So instead of maybe doing a day worth of data in each chunk, you do 24 hours, or sorry, if you had a week before, you do a day now. And if you want to change maybe how you partition in the space dimension, you go from maybe 4 to 6 partitions or any other number. Now, some of you might think that, well, if I change the partitioning, what happens then with the existing data? We actually don't do anything with the existing data because it's partitioned already and we created those tables, so they stay the same. Because we have constraints on these tables saying which time interval they contain or which space partition they're part of. So we can't easily change this, and rewriting this would be very costly. But here again, we're kind of saved by the fact that you're moving forward in time, so eventually you will sort of move out of this window where you have the old partitioning into the new partitioning scheme. And further, some of you might think that, well, won't there be like conflicts between how you partition? If you repartition and change the scheme, won't there be conflicts between the old and the new? And yes, it can happen. Like if you change the size of a chunk and make them much, much smaller, there might be conflicts like shown here in the picture. But in our database engine, we do what we call conflict resolution. We basically do the same thing you do in a computer game when you do bounding box detection to find that something is colliding. And then we detect a collision and we cut that chunk to fit within the new partitioning scheme. So what happens here is that when you're changing the partitioning, at that point when you're actually changing, you might see some chunks that are small or very small, depending on how they conflict with the old scheme. But that, again, will sort of, once you move forward in time, that will be in the past, and maybe at some point you drop that data. So what are the benefits of all of this chunking? Well, the first key point here is that chunks will be right-sized, so they will fit in memory, or maybe you have the past, or the most recent couple of chunks will fit in memory so that they're warm and you can query them fast and you can insert fast. You can also do things like efficient retention policies. So instead of going into a table and doing row-by-row deletes, you can drop at the granularity of a table. And if you're familiar with Postgres, you know that if you go in and do a row delete, it's actually not deleting the data, it's just sort of marking it as garbage. So to reclaim that space later, you have to run a garbage collection process called vacuuming. And that's a very costly operation. Again, you're kind of rewriting the table to reclaim that space. So by dropping entire subtables, you avoid that vacuuming cost. And it's very fast, a lot faster. You can also scale up by adding disks. So here, if you start with a couple of 100 gigabytes and eventually you run out of disk space, you can just continuously add new disks because our database engine kind of supports sort of moving and spreading chunks across different disks automatically. You can also leverage this to do more parallelization. So Postgres has support for parallel queries. So obviously, if it's doing parallel queries across chunks on different disks, you will get better read performance. And the same is true for inserts. For the multi-node case, and this is something that we're developing currently, a scale-out version of TimescaleDB. So this chunking and spreading chunks across disks lends itself very well to also a cluster scenario, where instead of placing on different disks, those disks might actually be on different physical servers. So you can spread chunks across different servers to sort of scale out horizontally. And you can do a bunch of interesting query optimizations. You can do partial aggregates on each server, so you compute like a partial average, you send the partial result to some kind of front-end query server where you compute the final result. And so you can sort of distribute that workload across the cluster. You can also do things like replication. So a naive way of doing this is just to write the same data to multiple identical chunks across the cluster. You could also do things like leveraging the built-in streaming replication in Postgres. So there are different ways of doing this. But the key point here is that you can use this to implement high availability. So if a server goes down, you can just fall over to another server that has the same copy of that chunk. Or even if you don't have a failure scenario, you can spread reads across different nodes because they have the same information. So if you're querying multiple clients querying the same data, you can spread them across the load across different servers. So I want to talk also about some of the query optimizations that we've built on top of this. So here's the first one, which is quite important. This is actually something we're leveraging that's part of Postgres. So it's called constraint exclusion. So this is a way to look at the query if you have some kind of constraint in your query and say like, okay, we're querying all the temperature readings from a particular device. Then obviously there are some chunks in your system that might not have data for that device if you're partitioning on a device. So you don't want to query those chunks at all. You want to exclude them, and that's what constraint exclusion does. So in this case, you might actually sort of home in on the exact partition where that data resides. So you don't have to even look at the other data. Again, you can do that also in the time dimension. So here you might query all the nodes or disks or whatever just for the first chunk. You can, of course, have a query on both time and device and home in maybe on just one single chunk. So that's obviously going to make the query a lot faster than scanning the whole data set. Here's another interesting query. So sometimes you want to do a query like this to query the past day worth of data. So the difference here is that you're using a non-constant time expression. And here, plain Postgres can't exclude any chunks because it's doing this at the planning stage. And because it cannot cache that query, because every time you run that query later, it will compute a different timestamp, right? So you can't cache that query. So it can only compute that timestamp when it's actually running the query and not planning it. So in this case, Postgres was just scan all the data. So we had an optimization here to improve this to actually do the exclusion at runtime. Here's another interesting optimization. In time series data, it's very often you very often want to sort of group by time. You want to do time bucketing. Maybe you want to compute the average every minute or so. So in this case, in this query, we want to return the most recent time buckets with the average CPU. And in this case, since you're looking for the most, the 10 most recent buckets, there's a requirement that you have some kind of ordering to know which ones are the most recent ones. But here's a problem, because you want to query in the time dimension, but you're doing an expression on time with this date trunc function where you're doing the bucketing. And then Postgres can't map that to an index on time. So it can't use that index. So again, it turns into this full scan and then a sort of this data. But we've added an optimizations to make Postgres understand that if we're computing this bucket on time, those buckets are going to have the same ordering as the time, the sort of raw time column. So we can actually make use of that index to order the bucket anyway. So you don't have to create another index for that date trunc function. If you have lots of indexes, that's obviously going to be bad for your insert performance. And insert performance is really important with time series data. We've also done another optimizations for querying many chunks. So as I said before, we're dealing with thousands of chunks in this type of workload. And we found that a lot of time was spent actually in the planning stage trying to figure out which chunks to query. And again, we found that Postgres isn't really optimized for this case because it was opening all the subtables just to get some statistics. And those statistics aren't really needed if you're just looking at one or two chunks. So you're paying that cost to open all the subtables just to look at one chunk. And that's not good. So we added optimizations to sort of redo that chunk exclusion ourselves with our own system. And that reduced the planning time for this particular query with 4,000 chunks from 600 to 36 milliseconds. So is it just about performance? Of course not. We've implemented a bunch of sort of convenience functionality or functions that are useful for doing time-based queries. So I've already mentioned some kind of time bucketing, which is common. So we implemented our own version of time bucketing that's more flexible than the provided date trunc that's in Postgres. We've also implemented other functions like getting the last value from a column, for example, which is also common in time series-based queries. So there are a bunch of these sort of convenience functions, and we're continuously adding more functionality based on maybe user input or like requests from various companies that are doing interesting things with time series data. Another example is how you can use our extension together with other extensions, because there's a rich ecosystem out there with extensions for Postgres. So a very useful common one, which is great together with time series data, is PostGIS for geographical queries. So here's a query with time bucketing and a geographical query to sort of get the number of trucks that's moving out of a geographical area each day, and the tonnage that translates to. So that can be a really useful query to do. And you can also connect TimescaleDB to your favorite dashboards. In particular, we have great support for Grafana, which is very popular today. And in fact, the guy who implemented the data source connector for Grafana, he's actually a timescaler himself. And in a recent version, he implemented a graphical query builder. So you can now easily create your SQL queries using this graphical interface. So this works really well for sort of simple queries. Typical, you want to do roll-ups on a single column or something, or do some simple visualization. But if you want to do something more advanced, you can, of course, just write your own SQL, or you can use this as a template and then sort of modify it. And finally, I want to spend some time talking about what we're working on next. So I've already touched on this briefly. So you might want to do continuous aggregation. So if you're sampling data at a sort of fine-grained interval, you get some raw data, and you might want to downsample it to save some disk space or make queries faster. So we want to automate that. So you can sort of downsample to minute worth of data, for example. But you can keep the most recent data using, in the raw format. So you have very sort of fine-grained resolution there. Again, we want to build a scale-out version of this where you can involve multiple nodes. So here we imagine that you would have one or a set of front-end nodes to which you connect as a client, and you write your data there. And this is going to present a very sort of familiar interface. It would look like any kind of single node TimescaleDB database. And then we're doing writes to the backend, and here we're using two-phase commit to ensure that we retain transactional semantics, so it's all or nothing. And of course, if you're doing reads, we can do a bunch of query planning at the front end. So again, we want to exclude chunks at this stage, because that translates to actually excluding entire data nodes, so we can avoid actually reaching out to some nodes that doesn't have any data for that particular query. So we only go to those nodes that actually have the data. Then you might do things like tiered storage. So you might want to keep your most recent data on a fast SSD to have fast writes, fast queries. But as time goes on, you can maybe move your older data to slower disk, maybe a magnetic disk. And eventually, maybe you want to just archive it for longer term storage. So this is something we also want to make easy in TimescaleDB. And again, we just released our 1.0, so we're production ready, and we're working now towards adding some of the functionality I've been talking about. So if you're interested in learning more about this, I'm available today if you want to talk to me about more about what we're doing at Timescale. And that's pretty much it for me today. So I don't know if you have any questions. I'm happy to answer them. Thank you.